The gene control game. When people hear the phrase gene control, they usually imagine repairs, fixing a broken gene, editing a bad sequence, or swapping in a better version. It sounds like correcting a blueprint, but biology isn't a frozen diagram. It's a moving system, always shifting and redefining itself. And because it never sits still, it behaves much less like a machine and much more like a game that's always in motion, always updating its state. If we want to guide it, we have to learn the rules of that game, and the only way to learn the rules is to play. In this video, we are going to use this game analogy to show where all the pieces from this gene control series fit into the big picture. Every move changes the board. Once we see biology as a game, the next thing we notice is how active it is. Every molecule, every pathway, every signal is a move on the board, and every move reshapes the system, even if only a little. When we act, biology responds. When biology responds, we learn something new, and this cycle never ends. It's a complex, dynamic game that keeps updating itself, turn after turn, whether we're paying attention or not. The challenge isn't to stop the game, it's to understand how to play it. Seeing the board. To play any game, the first thing you need is a clear view of the board. Biology is no different. Every tiny signal the body sends is a move the system is making, and to guide that system, we have to be able to see those moves as they happen. That's the job of molecular sensors. They watch the body's chemistry in real time, catching the small shifts we depend on. Without this visibility, we can't even start to play. But with sensors sharp enough to read the tiniest signals, we can finally see the board, and we can see how the system is moving and responding. Learning the rules. Once we can see the board, the next question is simple. What do all these tiny moves mean? That's where AI comes in. Molecular signals form patterns that are far too complex to map by hand, but AI can sort through them easily. It looks for relationships, correlations, and recurring moves across billions of data points. From those patterns, it begins to outline the rules of the game, the quiet rules that control how the system responds. And once those rules start to take shape, AI can begin generating many small, exploratory gene controllers, variations built from what it already knows, to probe new parts of the game and keep expanding the map. Keeping the game safe. Once AI begins generating exploratory controllers, the next question is how to test them safely. That's where microtesting comes in. Instead of large, risky interventions, we make tiny, controlled changes, just enough to see how the system shifts. And when millions of people run these small tests, capturing the results with high-resolution sensors, the outcome is a massive stream of data. Each microtest is a safe move in the game, and together they map the space far faster than any single lab ever could. Microtesting is what turns exploration into a scalable, low-risk process. It lets us learn the game safely, one tiny move at a time. Playing for the win. Every tiny move we make sends a ripple through the system. Biology responds, the board shifts, and new signals appear. High-resolution sensors capture those shifts and feed them back into the loop. Where AI learns a little more, new controllers are generated, and microtests explore the space a little further. This is the full cycle we've been building toward, a continuous, automated loop of sensing, learning, testing, and responding. It's the heart of an information systems approach to solving problems at massive scale. Thank you for following this series. I hope this framework gives you a simple way to see how all the pieces fit together, and a clearer sense of where gene control may be headed.